Hello, everyone. My name is Manager Wafi. I am with the Gyrfalcon technology or GTI, responsible for advanced technologies in the company. Also, I am a co-chairing MPEG-VCM, video coding for machine. The title of the presentation is CDVA and VCM, a language for intelligent and autonomous vehicles. This is a part of the session of advanced image video coding for machine vision. The authors of this paper are Bahua Sun, Hao Xiao, Manager Rafi, and Lin Yang. And I will be presenting on behalf of Bahua Sun on this paper. Before I get into the detailed discussion of this language so-called for intelligent transportation, I just want to give you some background, some precursor on video coding for machine as we know it. As many of you are aware, the CDVA has been around as a standard for a year or so. It became a standard recently in 2019 as a new standard for image and video search and analysis. And some consider that as a first generation of a language for image and video streaming. At the same time, about a year ago or so, another standard is emerging called MPEG-VCM, video coding for machine, which is a standard for developing advanced features beyond what we have for CDVA. This is, again, considered as the next generation for video coding for machine. The main two functions of VCM are feature extraction and then the feature compression in general. The VCM or MPEG-VCM attempts to kind of bridge the gap between the feature coding for machine vision and the video coding for human viewing purposes. CDVA, on the other hand, again, can go beyond what we know for analysis and search. And we have shown different variants of CDVA in different publications, as well as contribution to VCM, so-called SuperCDVA, closed caption CDVA, tied CDVA, bare CDVA, and a few others. Again, these are some variation of CDVA. How can we use this compact vector for other applications? Just want to show you the roadmap that we have for MPEG. As you notice that VCM is getting some momentum and attention. This one is part of the media coding, and then it is projected to go beyond 2024. And I highly encourage, already we have many experts participating from different companies, and highly encourage every one of you, you participate as well in this activity. Just to show you some scenarios, some application scenarios in real world. For this paper, we focus more on intelligent transportation, or if we want to generalize that, we can say it's intelligent robotic vehicles. In this case, part of that can be smart transportation, it can be ADAS, the higher layers of autonomous driving, for example, or it can be some connected cars or devices, or can be used for high precision map, even for a smart IoT, just all these devices be connected together. And one of the enabling technology for this can be 5G. We can use it as intelligent connectivity to put all this thing together or connect them together. Other application, of course, can be lawnmower, vacuum cleaner, security robot, and other robots that we can use inside the warehouses. It is important because for 5G, we have this V2X standard, that is, we communicate, a standard for communicating between two cars. If we have another standard, let's say a CDVA standard vectors, it is going to be easier for all these different manufacturer, vendors. They can talk the same language and understand each other and communicate. And you don't need to send a raw images, which is mostly very bulky and may not be very good for time-sensitive and latency-sensitive applications such as autonomous driving. Instead, you just send the vector, the CDVA vector, or you can compress it and send it to the other end, and the other end you can process that and decode it and use it for certain application. For example, for closed captioning, CDVA, or some other segmentation or other purposes. Or you can send it to the side road cell or to macro or macro cell that you have, and go to the whole network, 5G network, and broadcast this to the over the whole grid and go that way. This is some other good thing about this is like a safety. For example, the cars, if some accident happens, some event is going on, they don't need to be aware of that. They don't need to look at the image or video. They just, we can translate that into some caption and send it to the other side. And then through the text to speech, for example, or read aloud, that can be read back to the driver or passengers. Or if there are some alerts you want to send it to a group of people, you can use that. This way, you don't need also to use so much extra video transmission bandwidth that normally is used if we use this method. Just to give you some analogy between what we mean by video understanding before we can get more deeply into the discussion. The analogy is a natural language processing or natural language understanding. In general, what we do, if you have a sentence, let's say we have welcome to ICIP 2020 meeting, normally what we do, we get that in, and then try to break it down into some tokenized into separate words, each one of them, and then process them independently. In some cases we did before, we use all these different words, and then we convert that into two-dimensional embedding images, and then feed this into some CNN model in order to classify what is happening. By doing that, we actually obtain some state-of-the-art result compared to other benchmark data sets. All these references are provided in the paper as well. And we call that a super character when we did that. You want to use the same method we use for kind of NLU or NLP, and then use that, apply the same methodology for the video on the right-hand side. This is a video understanding. Again, we need a sequence of frames, but these frames that we have, we can interpret that as frames as some word, but we convert those words using a CDVA or compact descriptor for video analysis into a separate vectors of a 1, 2, or 3. For example, these are 3 different frames that we have here, and then each one of them entry is composed of a string of different numbers. So as we have here the sentence decomposed into word and decomposed into letters, here we have the vectors decomposed also into different numbers. The only thing is that CDVA, again, depending on what we are operating on, the limit, for example, is 512 numbers that we have in there. Again, by combining the CDVA vectors from multiple frames in order to represent a frames, we use another model that I'll explain in a minute, that is understanding what we do here, and then going to next slide, and then create something we call SuperCDVA. Then we can analyze and interpret the video. In this example, let's assume that we have some data input, some clip composed of multiple frames. Let's say we get 4 frames of this video, and then we use MPEG-CDVA standard as it is, extract all these features, put them into 4 CDVA vectors. As we explained in the previous picture, this one is 512 by 1 vector that we have after nested invariant pooling that we do. And then the CDVA vector is then it's quantized into a pixel intensity in the range of 0 to, let's say, 255. And then we embed that into each one of them into one block in an image. In this case, we have 4 blocks corresponding to 4 CDVA vectors. So the accuracy from the experience that we have is going to be increased if we use square blocks. That's why each one of them put it there. In this case, if we have 112 by 112, let's say image, each one of them is 56 by 56 pixel area. And we call this as SuperCDVA, basically, what we have image. Then we process that through some CNN model. In this case, we're using some chip in real time. And then the output is prediction of the sentence, or the, in this case, the video, what is happening in this video. Now, we use this with some other method, which is the closed caption method. In this case, we have some video clip again. We use CDVA to extract, as we saw before, the CDVA vectors, and then we quantize them and then put into the pixel intensity. We use that as an upper portion of this image. So the upper portion only is the vectors. It is a picture, a pixel of the CDVA. The load is nothing. We process the whole thing into a CNN model. And based on what you see from the previous slide, the super character, we predict what the first word is. Then we get that and reshape that into so-called a squared English word. Again, that is the reason we do that. The accuracy is increased dramatically by doing that. And then we get this image and then process that, and we continue. Again, this is the 512 by 1 vector that we have, and we reshape that into 16 rows of 32 entries, and each entry is 7 by 7 pixels. And then by that, the whole together generates 112 by 224 image on the upper side, and the other one also is going to be the words that we put in there. So the whole thing is going to be 224 by 224. And then through some criteria, depending on when we stop, if we predict, let's say, EOS, which is end of sentence, we stop, or if we reach the maximum words in there, we can stop the process. As I mentioned, this is used for robotic vehicles. There are many applications for ADAS or autonomous driving. It can be for robotics, indoor and outdoor, warehouses, vacuum cleaners, etc. And these can be connected to each other and talk to each other by the way. The experiment we did, we took 7 trips along the same trajectory. We collected 7 different batch of data. And then for that one, we use 6 of them for training and 1 of them for testing. And the video clips, each one of them for indoor or outdoor, we use a continuous 64 frames, and each frame is labeled with the next action that taken. The action was either go forward, turn left, or turn right, again for indoor and outdoor application. And the 64 frames, it was processed at 30 frames per second, roughly for 2 seconds. Then for the result, for the outdoor navigation, the model we use was GNet FC. It is a minor modification of BGG network that we use for our chip. And then we process it for 20 milliseconds inside our chip. The accuracy we got from testing was 94.3%. And the incorrect label mostly happens when we have a transition of going from forward to turning left or right. For indoor navigation, we use the ResNet 50 model. The accuracy for that one was slightly better, 96.5. As you can see on the lower corner, we have the data size for different classes of application, forward, left, and right, and for indoor and outdoor, and for train and testing, as you see it here. Finally, these are the results of what we have seen. This one is on the dashboard, we have the camera, and this is the legend or caption of what is happening in the video when we go forward, and or we turn right, or other cases, or left. It can predict you with high accuracy. The middle one, it can be a robot that we have inside the building. Again, as you see, we turn right or left and go forward inside the office. And the other application that we use is not shown here, but for lane change detection also, we can alert other people that what action we are taking inside the road. Or it can be used for a sport understanding or video understanding what is happening inside the video. or what type of sport also you're doing in there. For example, if it is breast, stroke or other types, it can identify that, or front crawl. And finally, for image captioning, understanding of what is happening inside the image and describing the behavior. That's all I have. And I want to thank you, everyone. And please let me know if you have any questions regarding this presentation. Thank you so much, everybody.